In electrochemistry, we tabulate the various half-cell reactions relative to the standard hydrogen electrode. And here I've done that. I've taken the half cell for copper metal and copper ions and the half cell for zinc metal and zinc ions relative to the standard hydrogen electrode. I've arranged them from high potential to low potential, from large positive potential to large negative potential. In doing that, that tells me a few things. It tells me the potential for copper ions to accept electrons and form copper metal is high relative on this table. That means copper ions are relatively strong oxidizing agents. They're willing to accept electrons. So when copper ions are in solution and there's some metal there, it's likely for the copper ions to withdraw electrons and form copper metal. When they withdraw electrons, they're oxidizing that metal. The copper ions themselves are being reduced. Conversely, this zinc system would work the opposite way. When zinc metal is in contact with ions, the tendency is for zinc metal to give up electrons to those ions. So the zinc metal is a reducing agent. It tends to donate electrons, to give up its electrons, and thereby reduce something, while the zinc metal itself is oxidized. So this table of standard reduction potential gives us that predictive power of the relative oxidation and reduction strengths of various metals and ions. So I can write down now the reaction. I know if I have copper ions in contact with zinc metal, absolutely what's going to happen here is the copper ions are going to withdraw electrons from the zinc metal. Or I could look at it the other way and say the zinc metal is going to donate electrons to that copper ion. The zinc will be oxidized, the copper ions will be reduced, and the result will be zinc ions and copper metal. Now, I could do that in half cells. I could put the zinc and zinc metal in one half cell and the copper ions and copper metal in another half cell, connect them with a salt bridge and a wire, but this same overall chemical reaction will still occur. The potential, the voltage for that half cell will be the difference between the copper ion and zinc ion half cells. So I can take the right half cell minus the left half cell, copper minus zinc, and you can see that would be 1.1 volts. So the potential for this reaction to go should remind you of another thermodynamic parameter, the free energy. The potential for this reaction to go, the fact that it favors the products here, sounds like the free energy. And indeed, the potential is related to the standard state free energy difference. The standard state free energy difference is given by minus NF delta E, the potential difference. In this case, N is the number of electrons transferred in the process, in that case 2 electrons. F is Faraday's constant. That's the charge on a mole of electrons. So what we see is the free energy difference related to the voltage in a way we understand. A positive voltage, the potential for this reaction to go is positive, relates to a negative free energy difference. So our table of standard reduction potentials can be used to connect voltages with free energies, to make the connection between electrochemistry and thermodynamics.